originating from a time when the cosmos was only 730 million years old. Gamma-ray bursts occur when massive stars die, not ordinary deaths, but catastrophic collapses that form black holes or neutron stars. The infalling material releases tremendous energy, focused into narrow jets that punch through the dying star and blast into space. These events are so bright, they can be seen across the entire observable universe. They serve as cosmic beacons, marking the deaths of the most massive stars in existence. When astronomers detected this particular burst, they immediately recognized its significance. The redshift indicated extreme distance. This was one of the earliest stellar deaths ever witnessed. But detecting the gamma-ray burst was only the beginning. The real prize would be observing what came after, the supernova. Gamma-ray bursts are associated with a specific type of supernova called a hypernova, or broad-lined type IC supernova. These explosions occur when massive stars that have lost their outer hydrogen layers collapse and explode. The connection between gamma-ray bursts and supernovae was established through observations in the local universe. But no one had ever confirmed this connection at such extreme cosmic distances. The early universe was supposed to be different. Stars formed from pristine gas. Their deaths might have followed unfamiliar patterns. 110 days after the initial burst, the James Webb Space Telescope pointed at the location. Using its near-infrared camera, astronomers separated the fading light of the explosion from the dim glow of its host galaxy. They found a supernova. The brightness and spectral features closely match supernovae associated with gamma-ray bursts in the local universe. The physics appeared identical. Massive stars in the early cosmos died the same way massive stars die today. This confirmation carries profound implications. It means the fundamental processes of stellar death were already established when the universe was only 5% of its current age. The physics did not need billions of years to settle into familiar patterns. It was consistent from nearly the beginning. One researcher involved in the discovery described it as a smoking gun. The observation connects the deaths of massive stars with gamma-ray bursts across cosmic time. It demonstrates that the cycle of stellar birth, life, and explosive death was operating at cosmic dawn. But the finding also raises questions. Supernovae scatter heavy elements into space, seeding future generations of stars with the materials needed to form planets and potentially life. If supernovae were already common 730 million years after the Big Bang, the chemical enrichment of the universe was well underway. This connects to the oxygen detected in the most distant galaxy. The supernovae that spread that oxygen must have occurred even earlier. The first generations of stars were not just forming, they were already dying in spectacular fashion. The early universe was a violent place. Stars ignited rapidly, burned through their fuel in millions of years, and exploded. Their deaths fertilized the cosmos, preparing it for the complex chemistry that would eventually produce planets, oceans, and life. Speaking of planets, the James Webb Space Telescope has revealed worlds stranger than anything in our own cosmic neighborhood, including one that might rain diamonds from skies of pure carbon. What happens when a planet orbits a dead star? Not just any dead star, a pulsar, a neutron star spinning dozens of times per second, beaming radiation across space like a cosmic lighthouse. An object with the mass of our star compressed into a sphere the size of a city. The answer, it turns out, is something no one predicted. The James Webb Space Telescope has discovered a planet unlike anything ever observed. Its atmosphere defies every known formation mechanism. Its composition challenges our understanding of planetary science. And deep within its interior, diamonds might be forming continuously. The planet orbits a pulsar roughly 6,000 light-years away. It has a mass comparable to Jupiter, making it a gas giant by any definition. But its atmosphere contains no water, no methane, no carbon dioxide, none of the familiar molecules we find in gas giants throughout our galaxy. Instead, its atmosphere is dominated by helium and molecular carbon. Pure carbon, in forms designated C2 and C3 by chemists. These molecules are extremely unusual because, at planetary temperatures, carbon normally bonds with other elements. Finding pure carbon suggests an environment entirely unlike anything in our cosmic neighborhood. One researcher described the discovery as an absolute surprise. The collective reaction was disbelief. This is extremely different from what anyone expected. The planet is also misshapen. Gravitational forces from the nearby pulsar stretch it into a lemon shape. It completes a full orbit in under 8 hours, racing around its dead stellar companion at tremendous speed. The intense pressure inside the planet could cause remarkable transformations. Carbon, under extreme compression, crystallizes. And crystallized carbon is diamond. Scientists believe the carbon in this planet's atmosphere could be sinking into the interior, where crushing pressures transform it into diamond crystals. These diamonds would fall like rain, accumulating somewhere in the planet's depths. Diamond rain is not entirely new to planetary science. Researchers have theorized it might occur deep inside Neptune and Uranus in our own cosmic neighborhood. But this distant world takes the concept to extremes. The mystery deepens when scientists try to explain how such a planet formed. Normal planets form from the disk of gas and dust surrounding young stars. They inherit the chemical composition of their birth cloud, which typically contains abundant hydrogen, oxygen, nitrogen, and other common elements. A planet with pure carbon and helium cannot have formed this way. Pulsar planets are rare to begin with. Only a handful are known. They might form from the debris of the supernova that created the pulsar, or from materials stripped from a companion star, but neither scenario easily produces the observed composition. One proposed explanation involves crystallization processes unique to cooling compact objects. As the interior cooled over billions of years, carbon and oxygen separated. Pure carbon crystals floated to the top and mixed into the helium atmosphere. The oxygen and nitrogen somehow stayed behind. The physics is speculative. No one fully understands this world. What seems clear is that planetary diversity extends far beyond our imagination. The universe creates worlds we never conceived of. Gas giants with diamond interiors, lemon-shaped planets racing around stellar corpses, atmospheres of pure carbon under alien skies. But strange planets are not limited to exotic systems around dead stars. The telescope has found bizarre worlds much closer to home, including one that should have been stripped bare but somehow kept its atmosphere. Some planets should not have atmospheres. When a world orbits extremely close to its star, the intense radiation strips away any gases clinging to its surface. The stellar wind blasts particles into space. Ultraviolet light breaks molecular bonds. Over millions of years, the atmosphere evaporates completely, leaving bare rock behind. This is well-established physics. Countless examples confirm it. Small planets close to their stars are airless. Then the James Webb Space Telescope examined a planet called TOI 561b. This world orbits one of the oldest stars in the Milky Way. The star formed roughly 10 billion years ago, when the universe was less than 4 billion years old. Any planets in this system have endured unimaginable spans of time. TOI 561b orbits so close that its year lasts less than 12 hours. At that distance, the dayside temperature exceeds 2,000 degrees. The surface is molten. A global ocean of magma covers the planet, glowing orange and red under perpetual stellar bombardment. By every expectation, this world should be bare rock. 10 billion years of intense radiation should have stripped away any atmosphere long ago. The planet should be a scorched cinder, its original gases scattered across space. But when astronomers measured the planet's temperature, something was wrong. The dayside was cooler than predicted. Heat was being distributed away from the stellar-facing hemisphere somehow. Something was transporting energy. The only explanation is an atmosphere. Further analysis confirmed the presence of a thick blanket of gases above the magma ocean, not a thin wisp of rock vapor, a substantial atmosphere rich in volatile compounds. This is the strongest evidence yet for an atmosphere on a rocky planet outside our cosmic neighborhood, and it exists where no atmosphere should survive. One researcher described the planet as really like a wet lava ball. The atmosphere somehow persists despite conditions that should have destroyed it. How is this possible? The leading theory involves continuous replenishment. The magma ocean constantly releases gases. Volcanic activity on a planetary scale pumps volatiles into the atmosphere faster than stellar radiation can strip them away. This creates a dynamic equilibrium. The atmosphere is constantly being destroyed and constantly being rebuilt. It exists in a state of perpetual regeneration. The implications extend beyond this single world. If magma oceans can sustain atmospheres even under extreme stellar bombardment, then the range of potentially interesting planets expands dramatically. Worlds we dismissed as airless might actually maintain thin but significant gas envelopes. This matters for the search for life. Atmospheres regulate temperature. They shield surfaces from radiation. They enable complex chemistry. A universe with more atmospheric planets is a universe with more possibilities. But TOI 561b is not habitable. Its temperatures far exceed anything compatible with life as we know it. The interest here is scientific, not astrobiological. For hints of life, astronomers look elsewhere, to a world that has sparked fierce debate about what the telescope can actually detect, a planet where possible biosignatures have ignited controversy across the scientific community. Can the James Webb Space Telescope detect signs of life on distant worlds? This question has divided astronomers since the telescope began operations. The answer depends not just on the telescope's capabilities, but on what we mean by life and how confidently we can interpret chemical signatures across interstellar distances. In early 2025, a team of researchers made a dramatic announcement. They had found what they called the strongest evidence yet for potential biosignature gases in the atmosphere of an exoplanet named K218b. The planet orbits a red dwarf star roughly 124 light-years away. It is larger than Earth, but smaller than Neptune, placing it in a category called sub-Neptunes. These worlds have no analogue in our own cosmic neighborhood, making them particularly mysterious. K218b sits in its star's habitable zone, where temperatures might allow liquid water to exist. Some researchers have proposed it could be a Haitian world, a planet covered by a global ocean beneath a thick, hydrogen-rich atmosphere. Using new transit spectra from the James Webb Space Telescope, the team announced they had detected signatures consistent with dimethyl sulfide and possibly dimethyl disulfide. On Earth, these gases are strongly associated with marine biology. Phytoplankton produce them in our oceans. The implication was electrifying. If these gases exist on K218b, and if they cannot be produced by non-biological processes, they might indicate life. But the scientific community responded with intense skepticism. Other researchers argued the signal was too weak to draw definitive conclusions. The data were noisy. The detection was at the edge of what the telescope could measure. Alternative explanations could not be ruled out. Critics also questioned the Haitian world concept itself. Some argued K218b might not be an ocean world at all, but a mini Neptune with a thick atmosphere and no solid surface. Under those conditions, any biosignature interpretation would be meaningless. The debate highlighted the limits of current technology. The James Webb Space Telescope was not designed specifically for exoplanet atmospheres. It was conceived before the explosion of exoplanet discoveries. Now, scientists are pushing it beyond its original specifications, extracting signals from the noise at the very edge of possibility. More observations are planned. Additional transits have been captured and await analysis. The data might eventually clarify whether dimethyl sulfide truly exists on K218b. But even if the detection is confirmed, proving biological origin will be extraordinarily difficult. We would need to demonstrate that no abiotic process could produce these gases. Given how little we know about exotic planetary chemistry, that bar may be impossible to clear with current knowledge. Some astronomers see value in the controversy regardless of outcome. If the result is that the public becomes more cautious about future claims of life detection, that would not be a terrible thing. Science requires skepticism. K218b remains a high-value target for understanding sub-Neptune atmospheres. Whether or not it hosts life, studying its chemistry teaches us about planetary diversity and the range of conditions that exist in our galaxy. The search for life continues. Each observation brings us closer to answering the oldest question humans have asked: are we alone? But before we can answer that question, we must understand the environments where life might emerge. And the early universe held surprises that pushed the boundaries of what stars can be. What did the first stars look like? This question has haunted astronomers for decades. The first generation of stars, called Population 3 stars, formed from pristine gas containing only hydrogen and helium. They had no heavy elements to cool the gas efficiently, so they collapsed into enormous masses. Theory predicts they were giants, perhaps hundreds of times more massive than typical modern stars. These primordial titans would have burned hot and bright, flooding the early universe with ultraviolet radiation. They would have lived fast and died young, exploding as supernovae that seeded the cosmos with the first heavy elements. But no one has ever seen a population 3 star directly. They existed too early, too briefly, and too far away. By the time their light reaches us, they have long since died. The closest we can get is finding environments similar to the primordial conditions. Galaxies with extremely low metal content, where star formation might follow ancient patterns. The James Webb Space Telescope has found such a place. A galaxy called XL's 63107 sits at a redshift indicating we see it less than 600 million years after the Big Bang. It is tiny, measuring less than 200 light-years across. For comparison, the Milky Way spans 100,000 light-years. But what makes this galaxy extraordinary is its chemistry. It contains only 1.6% of the oxygen found in our star. This is among the lowest metallicity ever measured in any galaxy at any distance, and its stars appear strange. The spectrum shows signatures that do not quite fit standard models. The ionization levels are unusually high. The radiation is unusually intense. Something is producing enormous amounts of energetic photons. One interpretation is that this galaxy contains a top-heavy initial mass function. This means massive stars are more common than they should be. Instead of the normal distribution of stellar masses, this ancient system is weighted toward giants. If true, this has enormous implications for understanding reionization. Massive stars produce far more ionizing radiation per unit mass than small stars. A universe where early galaxies had top-heavy mass functions would have reionized much faster than one with normal stellar populations. Another possibility is even more exciting. Perhaps the conditions in XL's 63107 are so similar to primordial environments that it hosts stars resembling population 3 objects. Not the true first generation, which would contain 0 metals, but something close, a window into what the earliest stellar populations might have been like. The galaxy is forming stars at a remarkable rate given its tiny size, roughly 8 times the mass of our star every year, packed into a volume smaller than most star clusters. The intensity of this activity produces the unusual blue light detected in images. Scientists emphasize that more observations are needed. The interpretations are preliminary, but the discovery demonstrates that extremely primitive galaxies existed during the cosmic dawn, and the telescope can study them in detail. We are approaching the boundary of first light, the very first structures to emerge from the darkness. Each metal-poor galaxy brings us closer to understanding how the universe transitioned from primordial simplicity to the complex, enriched state we see today. But not all early galaxies were actively forming stars. Some had already stopped, and their premature dormancy creates another puzzle for cosmology. Galaxies are supposed to evolve slowly. The standard picture goes like this. Young galaxies form stars vigorously. Gas flows in, collapses, ignites. Over billions of years, the gas supply gradually depletes. Star formation slows. Eventually, the galaxy becomes quiescent, a red and dead system containing only old stars. This process should take many billions of years. A galaxy forming in the early universe should remain active for a long time before exhausting its fuel. The James Webb Space Telescope found galaxies that broke this rule. Deep in the early universe, less than 2 billion years after the Big Bang, astronomers discovered galaxies that had already stopped forming stars. They were dormant, quiescent. Their stellar populations showed ages indicating star formation had ceased hundreds of millions of years earlier. These galaxies were not supposed to exist. Scientists nicknamed them sleeping beauties, systems that fell into cosmic slumber far earlier than any model predicted. Their existence challenges our understanding of how galaxies evolve. The puzzle has 2 parts. First, these galaxies must have formed their stars extraordinarily quickly. To be quiescent by 2 billion years after the Big Bang, they needed to produce all their stellar mass within the first billion years. That is an astonishing rate of star formation. Second, something must have turned off that star formation abruptly. Gas supply must have been cut. Whether through consumption, expulsion, or some other mechanism, the fuel vanished. Several explanations have been proposed. Active galactic nuclei might be responsible. If a supermassive black hole at the center of a galaxy becomes extremely active, its radiation can heat surrounding gas and prevent it from collapsing into stars. The black hole effectively sterilizes its host galaxy, shutting down star formation through sheer energetic output. Galaxy mergers might also play a role. When galaxies collide, the resulting chaos can trigger intense bursts of star formation that consume available gas rapidly. The merger remnant then sits quietly, depleted of fuel. Environmental effects could contribute as well. Galaxies in dense regions of the universe experience different conditions than isolated systems. Gas might be stripped away by interactions with neighboring structures. But none of these explanations fully accounts for the observed population. The sleeping beauties are too numerous, too massive, and too early for any single mechanism to explain. The discovery adds to the growing evidence that the early universe was more dynamic than standard models predict. Galaxies formed faster. They evolved faster. They reached endpoints that should have taken billions of additional years. Something accelerated cosmic evolution, whether it was early dark energy, different dark matter properties, or physics we have not yet identified. The universe moved quickly from its primordial state to conditions resembling the modern cosmos. The sleeping beauties are symptoms of this accelerated timeline. They demonstrate that galaxy evolution was already advanced when the universe was a fraction of its current age. And they are not the only evidence of premature cosmic maturity. Spiral galaxies, those icons of organized structure, also appeared far too soon. Spiral galaxies are the crown jewels of cosmic structure. Their sweeping arms, elegant symmetry, and dynamic rotation represent billions of years of gravitational choreography. They are mature systems, products of extended evolution and stable conditions. Our own galaxy is a spiral. From our position within it, we see the band of light called the Milky Way stretching across the night sky. That band is the disk of our galaxy seen edge-on, packed with hundreds of billions of stars organized into graceful spiral patterns. Creating such structure requires time. Dark matter must accumulate into halos. Gas must settle into rotating disks. Density waves must propagate, triggering star formation along curved paths. The process unfolds over many billions of years. At least, that was the assumption. In early 2025, the James Webb Space Telescope delivered a discovery that challenged this understanding. A massive spiral galaxy, nicknamed the Big Wheel, existed within the first 2 billion years of the universe. The galaxy should have been elliptical. Massive early galaxies were expected to be smooth blobs of stars, their structures not yet organized into disks and arms. The violent mergers, thought to dominate early galaxy growth, should have prevented spiral formation. But the Big Wheel has clear spiral structure. Its arms are well defined. Its rotation is orderly. It looks like a galaxy from the local universe, not from the cosmic dawn. One researcher described the finding as remarkable. Having such a beautiful spiral structure means whatever processes built this galaxy happened in a very neat way. Either violent mergers did not occur, or most of the mass formed in place without major disruptions. The discovery joins a growing list of unexpectedly mature early structures. The spiral galaxy, Alaknanda, the numerous disk galaxies found at high redshift, the sleeping beauties with their already old stellar populations. A pattern is emerging. The early universe was not the chaotic, primitive environment we expected. It was capable of producing organized, sophisticated structures far sooner than models predict. This challenges fundamental aspects of cosmological theory. The hierarchical model of structure formation assumes small things form first and merge into big things over time. Smooth, organized structures should be late arrivals, products of extended peaceful evolution. But the observations show the opposite. Some of the largest, most organized structures appeared early. They beat the predicted timeline by billions of years. The implications ripple through every aspect of astronomy. Galaxy formation models need revision. Dark matter simulations need new parameters. The basic narrative of cosmic evolution needs updating. Some researchers suggest early dark energy might explain the accelerated structure formation. Others propose modified dark matter properties. Still others wonder if we are missing fundamental physics. No consensus has emerged. The debate continues. Each new observation from the James Webb Space Telescope adds evidence and complexity. What seems increasingly clear is that our picture of the universe is incomplete. The telescope has not just filled in details. It has revealed that the entire framework needs reconsidering, and so we arrive at the most unsettling conclusion of all. Everything we believed is being questioned. The timeline of cosmic evolution, the formation of galaxies and black holes, the nature of dark energy, the rate of cosmic expansion. The models that served astronomy for decades are failing to explain what the most powerful telescope ever built actually sees. This is not a minor adjustment. This is a fundamental reassessment. Consider what the James Webb Space Telescope has revealed in just a few years of operation. Galaxies appearing too early, too massive, too organized. Spiral structures existing billions of years before they should. Sleeping systems that stopped forming stars when the universe was still young. Black holes too large for their host galaxies. Objects feeding at impossible rates. A runaway supermassive black hole tearing through space at 2 million miles per hour, validating 50 years of theory with a single dramatic observation. Little red dots scattered across the early cosmos, now understood to be young black holes wrapped in gas cocoons. Perhaps an entirely new class of object called black hole stars. The seeds of the supermassive monsters that anchor every major galaxy. The epoch of reionization starting earlier than believed. Faint dwarf galaxies producing enough radiation to transform the entire universe. The first ionized bubbles, appearing just 330 million years after the Big Bang. The Hubble tension confirmed and deepened. The universe expanding faster than our best model predicts. Dark energy possibly weakening over time, throwing the ultimate fate of the cosmos into question. Exoplanets defying expectations. Lava worlds with atmospheres that should not exist. Lemon-shaped planets with diamond rain around dead stars. Potential biosignatures sparking fierce debate about whether we can detect life from light years away. Each discovery individually would be significant. Together, they constitute a revolution. Science advances through exactly this process. Observations challenge theories. Theories are revised or replaced. Understanding deepens. The cycle continues. But the current moment feels different. The anomalies are not isolated. They appear everywhere the telescope looks. Early galaxies, black holes, expansion rates, dark energy. The problems span multiple fields and point towards something missing from our fundamental picture. Some researchers believe early dark energy might unify several puzzles. Others propose modifications to dark matter. Still others wonder if general relativity itself needs revision on cosmological scales. No one knows yet. The data are still coming in. The James Webb Space Telescope continues observing, adding new discoveries weekly. Future telescopes will extend these findings, probing even deeper into cosmic history. What we can say with confidence is this: the universe is stranger and more dynamic than we imagined. It evolved faster. It created structure more efficiently. It harbors objects and phenomena that humble our theories. And this should excite us, not discourage us. The greatest moments in science come when observations outrun explanation. When nature reveals itself to be richer than our models captured. When we must return to first principles and think again. We are living through such a moment. The telescope 1 million miles from Earth has shattered our comfortable assumptions. The cosmos is not what we thought, but now we know what questions to ask. We know where the mysteries lie. We have clues pointing toward deeper truths. The journey of discovery continues, and whatever we find next will be stranger still. Some images define an era. In 1995, the Hubble Space Telescope captured a photograph that became one of the most famous scientific images ever taken. Towering columns of gas and dust, backlit by the glow of newborn stars, rising like cathedral spires against the darkness of space. The pillars of creation. For nearly 3 decades, this image shaped how humanity visualized cosmic birth. Countless textbooks reproduced it. Museum visitors stood transfixed before enormous prints. The pillars became synonymous with the wonder of space exploration. Then the James Webb Space Telescope looked again, and what it revealed transformed our understanding of what happens inside those majestic towers. The pillars sit within the Eagle Nebula, roughly 6,500 light-years from Earth. Each column stretches several light-years tall. For scale, the distance from our star to the nearest other star is just over 4 light-years. These are structures of almost incomprehensible size. Hubble showed us their beauty. Webb showed us their violence. In near-infrared light, the telescope pierced the dusty exteriors that had hidden the pillars' interiors from view. Suddenly, astronomers could see deep inside the columns, and what they found was chaos. Newborn stars by the hundreds, fiery jets blasting outward at supersonic speeds, shock waves rippling through the gas. The pillars are not peaceful nurseries. They are battlegrounds where gravity wages war against radiation, and new stars claw their way into existence. A research team studying the Webb data identified 253 young stellar object candidates within the pillars. These are protostars, objects still gathering mass from their surroundings, some only a few 100,000 years old, cosmic infants by any measure. But the most striking finding was where these infant stars cluster. They concentrate along the edges of the pillars, not randomly distributed throughout, and their ages appear to decrease with distance from the massive stars, illuminating the nebula. This pattern tells a story. The intense radiation from nearby mature stars is sculpting the pillars, eroding them like wind-carving sandstone formations in a desert. But as the radiation compresses the gas at the pillar edges, it also triggers gravitational collapse. The pillars are being destroyed, and their destruction is creating new stars. This process, called triggered star formation, had been theorized for decades, but never observed so clearly. The Webb data show it happening in real time. Star formation rates within the pillars have increased dramatically over the past million years, precisely as the erosion intensified. The wavy patterns along the pillar edges that look like glowing lava flows are not decoration. They are the supersonic jets from newborn stars smashing into the surrounding gas. Each collision creates bow shocks, rippling patterns of heated material that trace the violence of stellar birth. One researcher described the images as practically pulsing with activity. These young stars, perhaps only a few 100,000 years old, are announcing their arrival with spectacular violence. But there is tragedy hidden in this beauty. The same radiation triggering new star formation is also dooming the pillars themselves. Eventually, the columns will be completely eroded away. Their constituent gas will disperse into space. The stars they spawned will drift apart. The pillars of creation are temporary structures, monuments to a moment in cosmic evolution that will pass. In perhaps 100,000 years, they will be gone entirely. We are fortunate to witness them while they still stand. And yet, while we study stellar nurseries in our own galaxy, the telescope has also turned its attention to mysteries much closer to home, including the most distant planet in our cosmic neighborhood, where light dances in ways no one expected. For 30 years, astronomers searched. They knew auroras should exist on Neptune. Every other giant planet displayed them. Jupiter's auroras blaze hundreds of times brighter than Earth's. Saturn wears luminous halos around its poles. Even distant Uranus glows with faint northern and southern lights. But Neptune refused to reveal its secret. When Voyager 2 flew past the ice giant in 1989, instruments detected tantalizing hints of auroral activity, but the technology of that era could not confirm or characterize what was happening in Neptune's upper atmosphere. Ground-based telescopes tried for decades afterward. The Keck Observatory in Hawaii pointed its massive mirrors at the distant world. The Very Large Telescope in Chile searched through the infrared. Nothing definitive emerged. The problem was distance. Neptune orbits 30 times farther from our star than Earth does. At such vast separation, the faint glow of an aurora is extremely difficult to detect against the overwhelming blackness of space. Then the James Webb Space Telescope took its turn. In June of 2023, astronomers directed the telescope's near-infrared spectrograph toward Neptune. They were originally planning to study the planet's atmospheric circulation. What they found instead astonished them. Clear, unmistakable auroras, glowing cyan splotches of light high in Neptune's upper atmosphere, the first confirmed detection of auroral activity on the solar system's most distant major planet. One researcher who had spent years searching for this signal described being stunned by the detail and clarity. After decades of failure, the discovery came almost casually, during observations intended for different purposes entirely. But the auroras themselves presented immediate puzzles. On Earth, auroras cluster around the magnetic poles. Charged particles from our star spiral along magnetic field lines and strike the upper atmosphere near the Arctic and Antarctic. The collision excites atmospheric gases, which release energy as the shimmering curtains of green and red light we call the northern and southern lights. Neptune's auroras appear nowhere near its poles. They glow at mid-latitudes, the planetary equivalent of South America or Southern Africa. This bizarre location results from Neptune's extremely tilted magnetic field, which is offset by 47 degrees from the planet's rotation axis. Why Neptune's magnetic field is so misaligned remains unclear. The planet rotates on an axis tilted only 28 degrees from vertical, nearly identical to Earth's axial tilt. But its magnetic field points in a completely different direction, as if the planet's magnetic and geographic personalities are entirely disconnected. The Webb observations also revealed a critical chemical signature. For the first time at Neptune, astronomers detected trihydrogen cation, a molecule designated H3+. This ion forms when charged particles smash into hydrogen-rich atmospheres and serves as a definitive marker of auroral activity. Scientists had detected trihydrogen cation in the atmospheres of Jupiter, Saturn, and Uranus. Its presence at Neptune was expected, but had never been confirmed until Webb looked. Perhaps most puzzling was what the data revealed about Neptune's temperature. The planet's upper atmosphere has cooled dramatically since Voyager flew past. Several hundred degrees colder than measurements from 1989 suggested. This dramatic cooling may explain why the auroras remained hidden for so long. Colder temperatures mean fewer energetic particles, fainter emissions, and signals buried below the detection threshold of every instrument that tried before Webb. But why has Neptune cooled so much? The planet sits so far from our star that seasonal changes unfold over decades. Weather patterns may shift on timescales longer than human careers. Astronomers now plan to observe Neptune throughout an entire solar cycle, 11 years of study that may reveal how the distant world responds to changing conditions flowing outward from our star. Every answer the telescope provides seems to generate new questions. And closer to home, in the wreckage of a dead star, Webb has revealed structures no one anticipated. 340 years ago, a star exploded. The light from that catastrophic death reached Earth sometime in the late 1600s, though no contemporary observers recorded seeing anything unusual. The supernova's brilliance was apparently absorbed by thick dust clouds in the Milky Way before it could make an impression on earthbound eyes. Today, we call the expanding shell of debris Cassiopeia A. At 11,000 light-years away, it remains the youngest known supernova remnant in our galaxy, and the James Webb Space Telescope has transformed it into a laboratory for understanding how massive stars die. Previous observations from other telescopes revealed Cassiopeia A as a roughly circular bubble of hot gas, glowing in X-rays and radio waves. Hubble showed intricate knots and filaments in visible light, but Webb's infrared vision uncovered something entirely new. Deep within the remnant, projected against its interior, lies a structure no one had seen before, a thick sheet of material pockmarked with dozens of small, nearly circular holes. Because of its green appearance in the representative color images, astronomers nicknamed it the Green Monster. The discovery was completely unexpected. Supernova remnants are supposed to be hollow shells, the outer skins of exploded stars racing outward into space. The Green Monster sits in front of the main shell from our perspective, as if a veil had been draped across the cosmic wreckage. What is it? And where did those holes come from? Detailed analysis suggests the Green Monster is circumstellar material, gas and dust shed by the star before it exploded, now illuminated and sculpted by the blast wave that followed. The holes appear to be puncture wounds. Knots of high-velocity ejecta, chunks of the exploded star racing outward at thousands of kilometers per second, have punched through the sheet of circumstellar material like bullets through fabric. The research team measured more than 24 of these circular structures. Each spans roughly 1 to 3 arcseconds on the sky. If our star were placed at the center of one hole, its boundary would lie near the inner edge of our solar system's Oort cloud. These are not small features, but Webb's discoveries at Cassiopeia A extended beyond the Green Monster. The telescope revealed a web-like network of unshocked ejecta filaments, material from the exploded star that has not yet encountered anything to disturb it. These ghostly threads preserve information about the star's final moments, the turbulent mixing that occurred as the core collapsed and the outer layers were flung into space. Webb also detected remarkably bright carbon monoxide emission. This molecule forms in the cooling debris of supernovae, but had never been observed at such high temperatures. The finding indicates carbon monoxide is being created and destroyed simultaneously, chemistry in action amid the chaos of stellar death. One researcher described spending the rest of his career trying to understand what lies in this dataset. The images contain more information than anyone anticipated. Perhaps most intriguingly, Webb found what astronomers call baby Cassiopeia a small smudge of light, a light echo, sitting 170 light-years behind the main remnant. This echo is illuminated by photons from the original explosion finally reaching a distant dust cloud and warming it to visibility. Light echoes allow astronomers to study ancient events as if they happened recently. The echo from baby Cassiopeia A contains information about the explosion itself, information that has been traveling through space for centuries. Supernovae matter to all of us personally. They created the heavy elements that make up our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe. All of it was forged in exploding stars and scattered across the cosmos in events like the one that created Cassiopeia A. Understanding how stars die is understanding our own origin story. And as astronomers study the remnants of dead stars, they are also watching new ones being born. In the delicate process of planet formation, the telescope has witnessed something remarkable. How did our cosmic neighborhood form? 4.5 billion years ago, a vast cloud of gas and dust collapsed under its own gravity. At its center, a young star ignited. Around it, a swirling disk of material remained, the raw ingredients that would eventually become planets, moons, asteroids, and comets. We call this structure a protoplanetary disk, and the James Webb Space Telescope is revealing these cosmic construction sites in unprecedented detail. One of the most famous targets is HL Tauri, a young star roughly 460 light-years away in the Taurus star-forming region. Previous observations from the Atacama Large Millimeter Array showed concentric rings and gaps in the disk surrounding this infant star, suggesting planets might already be plowing through the material. When Webb turned its infrared instruments toward HL Tauri, researchers expected to see the disk, or perhaps detect forming planets within it. Instead, they saw something completely different, and it blew their minds. The telescope revealed streams of material flowing from the outer envelope of gas surrounding the young star down into the protoplanetary disk itself. Like rivers feeding a lake, these streamers carry raw material from the larger cloud into the region where planets form. We see a very complex and dynamic system, one researcher explained. Material flows from the outer envelope into the inner regions of the disk, where planets are being assembled. This process, called infall, had been theorized but never observed so clearly. The Webb images show it happening in real time. Our own cosmic neighborhood may have experienced exactly this kind of feeding during its earliest stages. But HL Tauri is not the only target. Webb has examined multiple protoplanetary disk systems, each revealing unique characteristics. Around the star MWC 758, previous observations had shown spiral arms forming in the disk. These patterns suggest a massive planet is orbiting somewhere within, its gravity disturbing the material like a spoon stirring soup. Webb's observations placed the most stringent constraints yet on where this suspected planet might hide. The data revealed no new planets directly, but the sensitivity is groundbreaking. Each non-detection narrows the possibilities, telling astronomers what kinds of planets can and cannot exist in these systems. In a separate breakthrough, Webb confirmed a long-proposed process of planet formation by observing water vapor in protoplanetary disks. The theory suggested that ice-coated pebbles drift from the cold outer regions of disks toward warmer inner zones. When they cross the frost line, where temperatures allow ice to vaporize, they release water vapor. Webb detected exactly this signature in compact disks around young stars. The observations represent the first direct confirmation of pebble drift, a fundamental process that may explain how rocky planets like Earth accumulate their mass. The telescope also discovered that protoplanetary disks lasted longer in the early universe than they do today. In metal-poor environments resembling conditions billions of years ago, disks around young stars appear to persist for extended periods. This extra time would have given planets more opportunity to form, potentially explaining some of the unexpectedly mature structures Webb has detected in ancient galaxies. Perhaps most surprising was what Webb found around brown dwarfs, objects too small to be stars but too large to be planets. In the Orion Nebula, the telescope confirmed that 20 of these failed stars possess their own protoplanetary disks. This means planets might form even around the smallest and dimmest stellar objects. The universe's capacity for world building extends far beyond what anyone imagined. Each observation teaches us something about how cosmic neighborhoods assemble. Every disk is a laboratory, every streamer is a clue, and sometimes the telescope spots the finished product directly, an actual planet, captured in its portrait for the first time. After 3 years of operation, it finally happened. On June 25, 2025, astronomers announced that the James Webb Space Telescope had discovered its first exoplanet, not by watching a star dim as a planet crossed in front, not by measuring gravitational wobbles, but by actually seeing the planet itself, glowing faintly in the infrared darkness of space. The world is called TWA-7b. It orbits a young star, 111 light-years from Earth, and it represents a milestone in the telescope's scientific legacy. Direct imaging of exoplanets is extraordinarily difficult. Stars are millions of times brighter than the worlds that orbit them. Their overwhelming light drowns out any faint planetary glow. Trying to see an exoplanet next to its host star has been compared to spotting a firefly next to a searchlight from miles away. Webb overcame this challenge using a coronagraph, an instrument that blocks out a star's light, like the moon blocking our star during an eclipse. With the stellar glare suppressed, faint objects nearby can emerge from the darkness. The Discovery team, led by researchers at the French National Center for Scientific Research, focused on young stars with debris disks that could be viewed face-on from Earth. This orientation allows astronomers to see the full disk structure rather than just its narrow edge. The star TWA-7, also known as CE Antilles, fit these criteria perfectly. Previous observations had revealed 3 distinct rings in its debris disk, with gaps that hinted at unseen planets sculpting the material. When Webb examined the narrow middle ring in June 2024, it detected a faint infrared source. After eliminating observation errors and confirming the detection was real, the team concluded they had found a planet. TWA-7b is approximately the mass of Saturn. This makes it 10 times lighter than any exoplanet previously captured in a direct image. The discovery demonstrates that Webb can detect worlds far smaller than the massive gas giants imaged by earlier telescopes. Computer simulations confirmed the finding. When researchers modeled a Saturn-mass planet at the detected location, the simulations produced exactly the thin ring and gap structure observed in the debris disk. The planet's gravity is shaping its environment in predictable ways. The world is young, likely only a few million years old. Because recently formed planets are still hot from the energy of their creation, they glow more brightly in the infrared than older, cooler worlds. This thermal signature is what Webb detected. One researcher described the discovery as likely just the beginning. The telescope has the potential to image even smaller planets in the future, perhaps worlds with only 10% of Jupiter's mass. This capability opens new frontiers. Previous direct imaging could only spot massive, hot planets orbiting far from their stars. Webb can now probe closer separations and smaller sizes, approaching the range where rocky worlds might eventually become visible. The finding also demonstrates that planets can shape debris disks in observable ways. By studying how disks respond to planetary gravity, astronomers can infer the presence of worlds too faint to see directly. TWA-7b will not be the last. The telescope continues examining young stellar systems, searching for the faint glows of newborn worlds. Each discovery adds to our census of planetary systems and reveals the diversity of outcomes when gas and dust collapse around infant stars. But while Webb finds new worlds around distant stars, it may have also discovered one much closer to home, a planet that appeared, then vanished, around our nearest stellar neighbor, 4 light-years. That is the distance to Alpha Centauri, the nearest stellar system to our own. In cosmic terms, it is practically next door. A trip at the speed of light would take only 4 years. At the speed of our fastest spacecraft, it would take tens of thousands of years, but at least the destination is conceivable. For decades, astronomers have searched for planets around these nearby stars. 3 confirmed worlds orbit Proxima Centauri, the faint red dwarf in the system. But Alpha Centauri A and B, the 2 bright stars that form a binary pair, have resisted planetary detection. In August of 2024, the James Webb Space Telescope changed that. Using its mid-infrared instrument and a coronagraph to block stellar light, astronomers detected a faint object near Alpha Centauri A, an object more than 10,000 times fainter than the star itself. The initial excitement was enormous. If this was a planet, it would be the closest to Earth orbiting in the habitable zone of a star similar to our own. A gas giant. Yes, but potentially surrounded by moons where liquid water might exist. Then the planet vanished. Follow-up observations in February and April of 2025 found nothing. The telescope pointed at the same location, used the same techniques, and saw no trace of the object detected months earlier. "We are faced with the case of a disappearing planet," one researcher exclaimed. The mystery sent astronomers scrambling to their computers. Using simulations that incorporated every piece of data, including observations from ground-based telescopes dating back to 2019, they modeled millions of potential orbits. The solution they found was elegant but frustrating. In half of the stable orbital configurations that matched all the observations, the planet would have been too close to its star during the follow-up observations to be visible, hidden in the stellar glare rather than absent from the system. Based on the brightness of the initial detection and the orbital constraints, researchers believe the object is a gas giant roughly the mass of Saturn. It orbits Alpha Centauri A on an elliptical path that brings it between 1 and 2 times the distance between Earth and our star. This orbit places the planet within Alpha Centauri A's habitable zone, the region where temperatures might allow liquid water on a solid surface. But as a gas giant, the planet itself could not support life as we know it. Any moons it possesses, however, are a different matter. The discovery, if confirmed, would be the closest directly imaged exoplanet, the coldest and oldest world captured in such a portrait, and the nearest habitable zone planet around a star resembling our own. But confirmation requires patience. The planet's orbit, if the models are correct, would bring it back into visible range in August of 2026. Astronomers are already planning observations for that window. The existence of such a planet in a binary star system would also challenge our understanding of planetary formation. The gravitational influence of 2 closely separated stars creates chaotic environments where planets were thought to have difficulty forming or surviving. If this world is real, it has persisted despite those challenges. One researcher noted that its very existence would force revisions to theories of how planets form, survive, and evolve in such environments. The waiting continues. The data sit in archives, analyzed and reanalyzed. The models run endlessly, testing every possible configuration. Is there a gas giant orbiting our nearest stellar neighbor? A world with potential moons where life might one day be found? The universe has answered with ambiguity, and so we watch and wait and wonder. Meanwhile, the telescope continues its search for atmospheres around small, rocky worlds, including the most promising candidate for habitability yet studied. 40 light-years away, 7 Earth-sized worlds orbit a dim red star. The TRAPPIST-1 system has captivated astronomers since its discovery in 2017. No other known system contains so many terrestrial planets packed so closely together. 3 of them orbit within the star's habitable zone, where liquid water might persist on their surfaces. Of these 3, TRAPPIST-1e has emerged as the most intriguing. Its size, mass, and density closely match Earth's. Its distance from its star allows moderate temperatures. If any world in this system could support an ocean, TRAPPIST-1e is the leading candidate. But there is a catch. For liquid water to exist, the planet must have an atmosphere. Without a blanket of gases to trap heat and regulate temperature, any surface water would freeze or evaporate into space. Does TRAPPIST-1e have an atmosphere? The James Webb Space Telescope has been working to answer this question since it began science operations. The results so far are tantalizing but inconclusive. Using the near-infrared spectrograph, astronomers observed TRAPPIST-1e as it passed in front of its star. This technique, called transmission spectroscopy, searches for chemical fingerprints in starlight filtered through a planet's atmosphere. If gases are present, they absorb specific wavelengths, leaving telltale signatures in the spectrum. The initial observations ruled out several possibilities. TRAPPIST-1e does not possess a thick, hydrogen-rich atmosphere like the primordial envelopes surrounding newly formed gas giants. If it ever had such an atmosphere, intense radiation from its active red dwarf star has stripped it away. This is not surprising. Red dwarf stars are violent, especially when young. They emit powerful flares that can blast away atmospheric gases over millions of years. The inner planets of TRAPPIST-1 have been subjected to this radiation for billions of years. But Earth-like planets can build secondary atmospheres. Volcanic eruptions pump gases from planetary interiors. Outgassing releases trapped volatiles. Our own world lost its primordial atmosphere and constructed a new one over time. The Webb data hint that TRAPPIST-1e might have done the same. Researchers detected possible signatures consistent with a nitrogen-rich atmosphere containing traces of methane. Such a composition would resemble Saturn's moon Titan, a world with thick haze layers and surface liquids. However, the detection is not definitive. The star, TRAPPIST-1, is extremely active, with surface features that contaminate the spectra astronomers are trying to measure. Separating planetary signals from stellar noise requires extraordinary precision and extensive observations. Additional observations are already planned. 15 more transit measurements have been scheduled, with astronomers hoping to build enough statistical confidence to distinguish real atmospheric features from noise. If successful, the detection would represent a historic achievement. The first confirmed atmosphere on a potentially habitable world beyond our cosmic neighborhood. A target for future observations, searching for biosignatures, the chemical fingerprints of life. One researcher described the work as pushing the limits of what the telescope was designed to do. Webb was conceived before the TRAPPIST-1 system was even discovered. That it can study these worlds at all is a testament to its remarkable capabilities. The search continues. Each transit provides more data. Each analysis refines our understanding. Somewhere in the noise may lie evidence that changes everything we believe about our place in the universe. And while astronomers probe distant atmospheres, Webb has revealed something remarkable about how stars themselves are born. A cosmic alignment that confirms theories physicists have held for decades. Sometimes the universe provides exactly the evidence scientists need. For years, astronomers had theorized that as interstellar clouds collapse to form stars, the resulting objects should spin in similar directions. Angular momentum, the rotational energy contained in a swirling gas cloud, should be conserved and passed down to the stars that emerge from it. But directly observing this prediction proved challenging. Young stars form shrouded in dust. Their rotation axes are difficult to determine. Confirming that multiple stars share aligned spins required seeing something that had remained hidden. Then, the James Webb Space Telescope imaged the Serpens Nebula. This stellar nursery sits roughly 1,300 light-years from Earth. It is young by cosmic standards, only 1 or 2 million years old. Stars are actively forming within its dusty depths, emerging from their cocoons into the harsh light of space. When Webb's near-infrared camera captured the nebula's northern region, astronomers noticed something remarkable. A group of protostellar outflows, jets of gas blasting from newborn stars, all pointed in the same direction. Typically, such jets have varied orientations. Each star should have its own random rotation axis, and its jets should align with that axis. Seeing multiple jets slanted the same way, to the same degree, suggested something deeper was happening. These aligned outflows are like sleet pouring down during a storm, one researcher explained. They provide a historical record of the fundamental way that stars are born. Young stars shoot supersonic jets from their poles as they gather mass. These jets collide with surrounding gas and dust, creating bright shockwaves visible in infrared light. The direction of each jet reveals the rotation axis of its source star. In the Serpens Nebula, a cluster of particularly young stars, some only about 100,000 years old, all share similar rotation orientations. They inherited their spins from the collapsing cloud that formed them. This confirmation has implications beyond basic physics. Aligned rotation might affect how planetary systems form and evolve. It might influence the likelihood of binary star formation. It might even affect the stability of any worlds that eventually emerge from the surrounding debris. Webb is a young stellar object finding machine, another researcher declared. In this field, we pick up signatures of every single young star, down to the lowest mass objects. The Serpens Nebula observations revealed other surprises as well. Filaments and wisps of different colors trace reflected starlight from protostars still embedded in their birth clouds. Diffuse orange regions mark dust sitting in front of these reflections. The image tells the complete story of star formation in progress. The telescope found stars at every stage of development, objects still wrapped in thick cocoons of material, stars just beginning to emerge, fully formed young systems already dispersing their natal clouds. Each observation adds to a coherent picture of how stellar nurseries operate. The process is messier than simplified models suggested, more dynamic, more varied. But fundamental principles, like angular momentum conservation, hold true. The universe plays by consistent rules, and those rules are becoming clearer with each image the telescope returns. From the Serpens Nebula to the Carina Nebula, stellar birth sites across the sky are surrendering their secrets. One of the first images the James Webb Space Telescope released changed how humanity saw the universe. The cosmic cliffs, a wall of gas and dust rising like mountains against a star-studded sky. Behind it, hidden from previous telescopes, lay something extraordinary, newborn stars by the hundreds. The image shows a region within the Carina Nebula, roughly 7,600 light-years from Earth. What appears to be a landscape of peaks and valleys is actually the edge of a massive stellar nursery. The cliff face marks the boundary between denser gas, where stars form, and the cleared cavity carved by radiation from mature stars. Previous telescopes could see the cliff itself, but could not penetrate it. Webb's infrared vision changed everything. Behind the curtain of dust, the telescope revealed protostars still gathering mass, objects that had never been observed before, wrapped in shrouds that blocked visible light but allowed infrared wavelengths to escape. Each glowing point marked a star in the process of being born. The image also captured jets and outflows from these hidden babies. Streams of material ejected at high speeds, colliding with surrounding gas, creating patterns that trace the violence of stellar formation. But the cosmic cliffs did more than reveal hidden stars. They demonstrated the interplay between destruction and creation that drives cosmic evolution. The radiation from nearby mature stars is eroding the cliff face. Gas boils away under the intense bombardment. Over millions of years, the cliff will retreat, exposing more of the dense gas behind it to the harsh stellar environment. As the erosion proceeds, it compresses gas at the boundary. This compression triggers gravitational collapse. New stars form precisely because the cliff is being destroyed. The same process operates in the pillars of creation and countless other stellar nurseries across the galaxy. Radiation from one generation of stars seeds the formation of the next. Destruction enables creation. The Carina Nebula is one of the largest and brightest nebulae in the night sky. It contains enormous quantities of gas and dust, enough raw material to form thousands of stars over millions of years. Webb's observations are mapping this inventory in unprecedented detail. Beyond the cosmic cliffs, the telescope has examined other regions within Carina. Each observation reveals new protostars, new outflows, new structures that challenge and refine models of star formation. The early release of this image was strategic. It demonstrated what the telescope could do. It captured public imagination. It announced that a new era of astronomy had begun. But the scientific value extends far beyond public relations. The data contain information about stellar masses, formation rates, chemical compositions, and evolutionary stages. Researchers will study these observations for years, extracting insights that illuminate how the galaxy renews itself. Every star that forms will eventually die. Some will explode as supernovae, scattering their heavy elements into space. Others will fade quietly into white dwarfs, their outer layers drifting away as planetary nebulae. A few will collapse into neutron stars or black holes. But from the debris of stellar death, new stars will rise. The cycle continues, has continued for billions of years, will continue for billions more. The cosmic cliffs show us one moment in this eternal dance. And the telescope that captured them continues its mission. revealing more with each passing day. 3 years. In just 3 years of scientific operations, the James Webb Space Telescope has transformed our understanding of the cosmos. It has challenged theories held for decades. It has revealed objects that should not exist. It has shown that the universe is stranger, older, and more dynamic than anyone imagined. But this is only the beginning. The telescope was designed to operate for at least 5 years, with fuel reserves that could extend its mission to 20 years or more. If nothing breaks, if the instruments continue functioning, Webb will keep observing for decades to come. What will it discover? In the near term, astronomers will continue probing early galaxies, searching for the very first stars and black holes to emerge after the Big Bang. They will map the chemical evolution of the cosmos, tracing how heavy elements spread from supernovae into new generations of stars and planets. They will study supermassive black holes at cosmic dawn, testing theories of how these monsters grew so massive so quickly. The heavy seeds hypothesis, black hole stars, direct gas collapse. Each prediction makes specific claims that Webb can evaluate. The mystery of the Hubble tension will receive continued attention. Is the universe expanding faster than our models predict? Is early dark energy the solution? Does dark energy change over time? The telescope's observations constrain these possibilities and may eventually force a resolution. Closer to home, Webb will continue examining exoplanet atmospheres. The search for biosignatures on TRAPPIST-1e and similar worlds represents one of the most profound scientific pursuits in human history. Finding evidence of life beyond Earth would change how we see ourselves forever. The candidate planets at Alpha Centauri and TWA7 require confirmation. Additional observations will determine whether these worlds are real or mirages created by noise in the data. If real, they become targets for intensive study. Webb will also keep watching stellar nurseries form new stars and planetary systems. Each protoplanetary disk reveals something about how worlds assemble from dust and gas. Each observation refines our understanding of our own cosmic history. The telescope's capabilities are still being explored. Engineers and scientists continue developing new techniques, pushing instruments beyond their original specifications. Discoveries still unimagined may emerge from these efforts, but Webb is not alone. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will complement Webb's observations with wide-field surveys. Ground-based facilities like the extremely large telescope under construction in Chile will provide additional perspectives. A new generation of astronomers is rising to interpret these observations. Students who were children when Webb launched will spend their careers analyzing its data, making discoveries that build on what we learn today. The questions Webb addresses are ancient. Are we alone? How did the cosmos begin? What will happen in the end? Humans have asked these questions since we first looked up at the night sky and wondered. Now, for the first time, we have instruments capable of providing answers. The journey of discovery is accelerating. Each observation reveals new mysteries. Each mystery drives new observations. The cycle feeds itself, pushing knowledge forward. We live in an extraordinary moment. A telescope floating 1 million miles from Earth is reshaping our understanding of everything. Stars, galaxies, black holes, planets, the expansion of space itself. The universe is not what we thought, but perhaps that is the point. Perhaps the greatest discoveries are the ones that force us to think again, to question assumptions, to rebuild our picture of reality from improved foundations. The James Webb Space Telescope has given us that gift, and the journey continues.